which you already know from the smaller grades. And we also discussed the nature of magnetic field produced by straight current carrying wire. So basically, what is Oersted's experiment? So what experiment Oersted did was he kept a magnetic compass near a current carrying wire. Okay. So what is the nature of magnetic compass? It always points in north direction, right? Which north? Geographical north. So let us say this is the magnetic compass. So this is what it is supposed to show. This is east, west, north, and south. So when he pass current through a conductor, imagine there is a conductor on your So you have, let's say this is conductor AB. Now if we keep the compass here below this, where is the compass kept? Below this. Initially, let us say there was no current. This was open initially. So the needle will be below the conductor. Now if the current is fast, so what will happen? How the current is flowing through the conductor? It's going down, right? So the needle now will be deflected in this direction. The compass needle will show in this direction. Okay, it deflects from the initial position north-south. Okay, this is when the compass is kept below the conductor. If you keep the compass above the conductor, then it deflects on the other side. It deflects like this. Okay, so there are two separate diagrams shown in your volume. One when the compass is kept below, and the other when the compass is kept above. Right? And when you increase or decrease the current, okay, the deflection increases or decreases. Okay? So what is the conclusion of Oersted's experiment? That a current carrying wire produces magnetic field. Otherwise, there will be no deflection in the compass. So originally, the compass is in the direction of Earth's magnetic field, which is very weak. Okay? But the local magnet has a stronger magnetic field. The magnet that you use in the lab has a magnetic field of around 1 Tesla. Whereas Earth's magnetic field is around 10⁻⁴ Tesla. Okay? So Earth has very weak magnetic field, but it is present everywhere on Earth's surface. That's why. And magnet has a tendency to align itself in the stronger magnetic field. Okay? So this is what it is. So then some other experiments were done to verify it further what is the nature of magnetic field. So the other experiment was this. I mean, I am attaching rheostat. Even if you don't attach rheostat, then you can have a constant magnetic field. Let us say now you have a current here. Did I show you on the monitor in the last class how to draw the magnetic field and all? Did I show the video? Yes. Okay. So now how the current is flowing? Current is flowing like this. Okay. So now, if you keep the magnetic compass here, again it should have shown here when the current was not flowing. But now when the current flows, it begins to point in some direction. Let us say right now here it points in this direction. Right? When you keep it at different positions, it keeps pointing and you mark a dot. Wherever it is pointing, you mark a dot. Okay? Like this. When you mark a dot on the direction in which the magnetic compass is pointing, that is the direction of magnetic field. Okay? So when you join the dot, it makes circle. Since the magnetic compass follows this path, you conclude that the magnetic field is circular. Not only circular, how? Where is it? It is in the plane perpendicular to the wire. Okay? If the current is moving like this, then the magnetic field is in the plane perpendicular to the wire, right? Like this. Let us say this is the wire, okay? So it is in this plane. Now concentrate. Okay. You can also sprinkle some iron powder, right? And after the current passes, you gently tap it. So the iron powder will arrange itself in the form of concentric circles. So iron powder is a magnetic substance, okay? Each iron particle acts like a magnetic compass. And therefore it aligns itself around the circle. Is that clear? So what does these experiments tell us? It tells us that whenever current flows through the wire, it generates magnetic field around it. And what is the nature of magnetic field? Nature of magnetic field is given by right hand thumb rule. Okay, or right hand rule, not right hand thumb rule. Right hand rule you can say. Or right hand thumb rule also. So what is right hand thumb rule? So when you hold the wire in your right hand, okay, such that the thumb is aligned in the direction of conventional current. Then these fingers, okay, are curled in the direction of magnetic field. So this is what it is. So this is the right hand thumb. Okay, understood? And this direction is of conventional current. So now this magnetic field is a vector field. At every point, its direction is changing, right? So what is the direction here? It is along the tip. You stop the tip of the finger. So wherever the tip is pointing, here it will be like this. Here it is towards me. Here, right, towards you, left. So at every point it is along the tangent. So whatever is the tangent here, you see, so magnetic field line is along the tangent. Did we discuss the properties of magnetic field lines?
Yes.
We have discussed already. So we have discussed quite a lot. Okay. And then finally, we are discussing different current configuration and what are the nature of magnetic field generated by it. Can you see? So magnetic field is a vector field. It has a value and direction. It has a magnitude and direction at every point. So where is it stronger? Where is magnetic field stronger? Is it same everywhere? It is stronger near the wire because the circles are more concentrated. Wherever it is more crowded, I have given you properties of magnetic field line. Wherever the magnetic field line is crowded, in that region, the magnetic field strength is stronger. What is magnetic field? So around every magnet, there is a region of influence in which any other substance experiences a magnetic force. So the region around the magnet, wherever any other magnetic substance experiences the magnetic force, that region is magnetic field for a given magnet. And how does the magnetic field strength behave? It is stronger near the poles of the magnet for a bar magnet. And in case of a wire, since the magnetic field is symmetric, it is stronger near the wire. As you go away from the wire, the magnetic field decreases. So to keep these things in mind. Okay. So are we good till here? What is right hand thumb rule and is it clear now? So what is the next topic? Then we also said two magnetic field lines cannot intersect each other. Why?
Because then we wouldn't know where the direction.
Yes, because we wouldn't know where the direction is. Right? Let us say the magnetic field is like this. So I said at this point, wherever we are calculating magnetic field, it is along the tangent. So at the intersection, you have two tangents possible on the curve. So which direction to take? We don't know. So this is not allowed. That's why magnetic field line cannot intersect. So it has a well-defined direction. That is only possible when the lines are separate. At any point, it is along the tangent. Okay. So next is, let's see this example. Example 12.1, page 158. What does it say? A current through a horizontal power line flows in east to west direction. Right? So you have a horizontal power line. Let us say this is example. So it is going from east to west. Let us say this is the direction of current. East to west. What is the direction of magnetic field at a point directly below it and at a point directly above it? So let us say this is the point below and this is the point above. Let's say the current I is going like this. This is A and this is B. So what is the direction of field?
Direction of field from north to south.
Apply right hand thumb rule. So you have to grip the finger around the wire. Huh? So when the thumb is like this, where is the fingertip pointing? Into the plane of mode. So that I told you, you show it as a cross. Tail of the arrow. The arrow is going into the mode. Okay? And this will be like, let's say this is the wire. So from below the wire, how it will be? Tip is coming towards you. So this will be dot. Tip of the arrow. So head of arrowhead, tip of the arrowhead, and this is the tail of the arrow. So cross and dot. Dot means field line is emerging. Cross means field line is entering. This is perpendicular. This is always in the perpendicular plane. Okay, is that clear? So that's it. So how it is happening now? It is emerging from here and it forms closed loops. It will form closed loop. Field line is never a straight line. It always forms closed loop. Like from your bar magnet field lines, you know that. What do you know? That field line emerges from the North Pole. Okay? It emerges from the North Pole and enters into South Pole. Out externally. Outside the magnet, this is the behavior. And inside the magnet, it is from south to north. This is how the loop is completed and it is 360 degrees around the magnet. So if this is the magnet, let's say this is North Pole and this is South. So field line is here. It's here also. It's here also. 360, full 3D space. It's not just in the plane of the board. Everywhere it is. Okay? Throughout. So likewise, we'll have field line here also. Okay, like this. So nowhere the field lines will intersect. So you can see the field lines are almost parallel to each other inside the magnet, right? But outside you see the distance between the field lines is not same, right? As it comes out, it spreads out. So maximum field strength is near the pole, and as you go away from the pole, and along this side also the field is weaker. Okay, full field strength is near the pole. Now the field strength is divided. You have half the lines on both sides. Here these are full lines. Is that clear? So wherever the field is concentrated, it is stronger. So is the answer clear? Read the answer. Is it clear? Example 12.1. In this chapter, you have only these kind of questions, no numericals here. You have to identify the direction of force, or direction of field, or direction of current. Okay, two things will be given. We'll see. Okay, now magnetic field in a current loop. So we'll see different current configuration and then we will see how the magnetic field is produced. Now imagine you have a current loop now. So how the current loop will appear? This is the current loop. Right? Let us say the current is entering from this side and coming out from here. You can do this by connecting the cell like this. Let's say we have a current loop like this. Again, how to find the magnetic field? So if you apply the right hand thumb rule here, it will form a concentric circle here. right? So the current is going up. So by right hand thumb rule, and just go on making the direction of magnetic. Okay. Likewise here also it will make concentric circles. Okay. So in this side of the wire, the current is in the downward direction. So again by right hand thumb rule, and likewise you will have concentric circle throughout the wire. In a plane, think of planes perpendicular to the wire. Everywhere this thing will be there. So there is magnetic field here also, everywhere. So there are two regions. One is inside the loop and one is outside the loop. So whenever the current is clockwise, right? What do you see? Likewise in the middle, like here, you can have a very big circle. The very big circle will be almost like a straight line. It will have a very large circumference, so it will be like a straight line. So in the middle, you can imagine that. Now you can imagine this as a plane, okay? This is a plane like this, perpendicular plane. So the plane can be imagined to be like this. Right. So it's like imagine this tabletop, okay? Two holes are drilled, and the loop is like going like this. Half of it is below the plane, the dotted part. Half of it is above. So the magnetic field line shown is only for one plane. One plane. The field line is everywhere. Are you with me? Give me your iCard. Okay, now this is the loop. Okay, right? So if the current is going clockwise like this. So when you apply right hand thumb rule, how is the field going? Everywhere inside. Correct? You just align the thumb, then the finger is going into the plane of the loop. This is what is happening. So right now what is shown is only one plane. So field is shown only in this one plane. So half of the loop is below the plane, half is above. Is it clear? Understood or not?
Yes.
Take a wire and so wherever you see the thumb, okay, where is the finger going? Inside. Right? So if you see from this side, okay, now this is the tabletop. If you see from your side, the field is going away from you into the loop. When I see from my side, I see that the field line is coming towards me. Okay, so the loop has two faces, one towards you and one towards me. So when the field line is entering, what pole is that? South. In the south pole, the field line is entering, and the field line comes out from North pole, right? So therefore, a current carrying loop is the smallest electromagnet. Understood? The current carrying loop acts as electromagnet. So when you see from this side of the table, this is south pole. Because the field is entering. So there is a sign convention. When the current is clockwise, wherever the current is clockwise, right, you match the direction of letter S. It acts as south pole. Okay. And when you see from this side, you will see that the current is anti-clockwise. That means the field is coming towards you. So that acts as north pole. Okay, so the current carrying loop acts as electromagnet. So as long as current is flowing, you will see the field lines inside. How these field lines are made? You can make use of a compass. Okay, with the help of magnetic compass, you can do that. Okay, so this is what it is. So in your book, what is shown is, now imagine if I turn it, right now you're seeing the face of the loop like this. Okay, now I turn it like this. Turn it by 90 degrees. Like the benches, the whole setup, the experimental setup, it's turned by 90 degrees. So you'll now see the cross section. How will you see? You will see the way it is shown in your book. Right? Now let us say the current is going from here. It is coming out from here. Right? So how the field will be? Now the field line will like this. Okay? Round, round, round like that. Are you with me? So it is continuous. So half the coil. So field line is entering into the coil and it is coming out. It's like this. So this is in one plane actually. This is, can you visualize? This is half of the plane. This is this side of the plane. Then it will be like this. And in between it is straight. Okay. Right. This side is basically, you can only see the front portion of the coil. If you see the section, only one edge will be visible to you. This is behind. This is behind. Okay, is that clear? So then this is how the field. Then this side will be south. This side will be north. So what did you learn? In a current carrying loop, whenever the loop, you're facing the loop, when the current going is clockwise. Clockwise current. Means south pole. Okay. South pole of electromagnet. So whenever you are seeing the loop and if the current is clockwise, that is south pole. And anti-clockwise current means north. Okay, so you will use this to identify the polarity developed in an electromagnet. Okay, so therefore, what did you observe here? Okay. So the conclusion is current carrying loop acts as smallest electromagnet.
The smallest electromagnet.
At least one loop you should have. नहीं तो कैसे होगा? Straight बार में तो north south pole नहीं बनेगा. Is there polarity in a straight current carrying wire?
Well, why is there not like there's a direction with where the current?
So how we have defined a magnet, north pole and south pole. From wherever the magnetic field line come out, that has to be north pole. Right? Wherever the magnetic field enters, that has to be south pole. When a straight current carrying wire, from where the field line is coming out and where it is entering, it is circular.
So the right hand comes over. The current goes from here.
So where is the start? Like if you have a bar magnet, you can designate two ends. So in a circular field, where is the start? Where are the two ends in a circle? Start.
Yes.
So a straight current carrying wire does not have pole, but a current loop has. So current loop has two faces, one on my side, one on the other side. So when you are observing it in front, okay, or you can observe this section. Then also you have left, right, front, back, or left, right. Depends how you are viewing it. Okay, you may not find the exact wording, so this is practical actually. This chapter is entirely experimental. So with this you will understand. So what if you change the direction? If you reverse the polarity, then what should happen? If it becomes anti-clock, so this is south, this is north in this situation. If you reverse the direction of current, this will become north and this will become south. Okay? So this is not possible with permanent magnet. But in electromagnet you can do that. Not only that, instead of one cell, if you increase the number of cells, then the magnitude of current will increase. So will the magnetic field strength. In permanent bar magnet, you have no way to increase the magnetic field strength. So in electromagnet, you have this flexibility. You can change the magnetic field, you can change the polarity, right? All those flexibility, and you can. The current loop acts as a magnet when you want it to. When you don't want to act it as magnet, just switch off the current. But with permanent magnet, you don't have that. It will always be a magnet.
In the left side of the loop, the magnetic field lines are in anti-clockwise, right? Then that should be the north pole.
So there are two regions, one inside the loop, one outside the loop. This is the pole. Now here, from here the field lines are going in, then they are coming out, then they are forming closed loop around the wire. And this is happening everywhere, no? But in a straight wire, how do you do that? In a straight wire, the field line will be cylindrical. Here it is not cylindrical. Here it is appropriately just like a magnet. Okay, it will take time for you to get used to it. Okay, so are you good till here? Now we are going to increase the number of loops. Okay, so what I am going to do is I'll take a hollow cylinder made up of plastic or cardboard. Now I'll wrap wire on it. What am I going to do? Wrap wire. Okay. So something like this. Okay. क्या हुआ था भाई?
वो वायर
तो पीसी पड़ गया था क्या?
ये कैमरा में देखो
फिर से हुआ डिस्टर्बेंस. देखो अभी इसमें when you have to wrap wire तो क्या करोगे? वायर अगर इधर से आ रहा है, ठीक है, तो लूप कंप्लीट होने के बाद it will be behind. तो one side is in front and the other side is behind. हमेशा ऐसे हो. When the loop is completed, it will go behind. Okay. Or if I am wrapping from behind, right? Let's say I start wrapping from behind. Then when the loop is completed, it will end in the front. So this care you have to take. So let us say I am starting the wrapping from the behind of the hollow cylinder. So this is how you will see. Okay. So I just need this cylinder to provide support for winding the wire. Later on, it is not required. So this is called solenoid or an electromagnet. So electromagnet when the current is passing through the coil. Okay. Otherwise, it is just a solenoid, right? So now tell me, if it is electromagnet, so how its polarity should be? What should be left hand and what should be right hand?
Left.
When you see from the left side, is it clockwise current or anti-clockwise current?
Clockwise.
Clockwise. So what pole it should develop? Clockwise is south pole. You just said, right? So clockwise will be south pole. And this will be north pole. Exactly. And if you see the magnetic field, it will exactly produce the magnetic field like your normal bar magnet. Okay. So there is no difference between a bar magnet and a solenoid in terms of the nature of the magnetic field, with a lot of added flexibility that you can increase and decrease the magnetic field strength in case of a solenoid. Right? So it produces similar magnetic field just like bar magnet. Okay, but it produces magnetic field as long as current flows through it. So the magnetic field strength can be changed. By increasing the number of turns. In the coil. Solenoid or coil. Current carrying coil. What is it? Current carrying coil. Current carrying coil. Okay. Increasing the magnitude of current. Okay, these are the two ways. What else can you do to increase the strength? ये जो core था ना core, after wrapping you can remove it. Then what is inside?
Air.
Air. So the core is air. So to increase the magnetic field, you can actually insert soft iron core. What can you insert? Soft iron core. Insert the explanation for this is in 12th standard.
So we could also just put another. So we could just also insert any other metal and it would increase.
Depends on the magnetic properties of the core. That is called core. There is something called as magnetic permeability. So different substances have different magnetic permeability, just like different substances have different resistance. So depends on that's rare earth. Have you heard about it? Rare earth
Yes.
metals. तो rare earth metals में ये सब आते हैं.
So they have low, very high permeability.
Magnetic permeability. So magnetization increases. That's how they create permanent magnets. You create a solenoid, inside that they will keep, and then flow the current for a very long time. Then that thing which you kept inside will get permanently magnetized. You should have thought about it, ना कि permanent magnet ऐसा natural तो है नहीं. Man-made permanent magnets are also there. So how are they made? Okay, so magnet is very essential component. Like all the odometer, speedometer, it has magnet inside. Without that, it will not function. Okay? Electricity production also requires magnet. So,
But sir, magnet production. Sir, magnetic field. Produce magnetic field, we need electricity.
yes, to produce electricity, we need sun, which is ever present. The primary source of energy is sun only. We are converting it into different forms. That's all we are doing in physics. So we have learned different techniques of harnessing energy. Nuclear energy is one of them. But it is very skilled knowledge is required to basically produce nuclear energy. So everybody cannot harness nuclear energy. There are less than 10 countries in the world who have developed the capability to produce nuclear energy. Because the challenge is after producing nuclear energy, if you don't manage it right, it could become Chernobyl or Japan. So many things have happened. So very skilled manpower is needed to handle it. Okay. So if you so here what you can do, change the direction, you can change the polarity. All that flexibility is here in case of electromagnet. So we are going step by step. First one loop. Now you can have multiple loops. How many loops are here? 8 loops are there. So it will produce 8 times the magnetic field strength what is produced by just one loop. Same current. Okay. So this is what it is. Next is we have 5 minutes, right? Huh? 3 minutes. Okay, just read till here yourself. So I will start the force on a current carrying conductor in a magnetic field in the next class. Next class will complete this chapter. We have only 2 topics remaining, and there are so many things which are not in your syllabus. Electromagnetic induction. Just write out electromagnetic induction from your volume. It's not there. So electromagnetic induction and Fleming's right-hand rule is not there. Okay, factors to increase. So this electromagnetic induction is completely not there. So what we have is only Fleming's left-hand rule and domestic electric circuits. Only these 2 topics. So next class I'll tell you what is.
Do you also have AC and DC?
That we covered briefly in the.
Oh yes, I was just asking.
No, it's not. It's basically production. How to produce DC current and how to produce DC. So DC is produced by
Just battery and
DC generator. No. That's DC generator and AC generator. But that is taken out from the syllabus. I don't know why they have taken it out. During Corona time they removed and now it's removed completely. It's very important actually. Although it will reappear in 11th and 12th. So what they have done is all the repetitive things they have removed completely. But it was good that it was introduced about it in 10th. So 11th, 12th it is easy. Their logic is not everybody follows science. Right? Some of them move to commerce. So why to torture them? But this is basic thing. Like everybody should know. This is general knowledge. Everybody in their life comes across magnet or magnetic toys, etc. So no harm in understanding this. Okay. So in the next class, I'll tell you what is the force acting on the current carrying conductor when it is kept in external magnetic field. Because you know that 2 magnets will repel or attract each other. Current carrying wire also acts as a magnet. If it is placed in another magnet, then some force will act. What is that?
ये क्या किया मेरे बाल के? अभी मैं ऐसे स्किन पे बल मारती है सीधा। स्किन पे मैं क्या कर रही हूँ? अगर लेक्चर में समझ मैं मुझे भूख लग रही है वो अलग।
Was this some party or something? DJ, हाँ DJ। हम लोग ने ना वही कपड़े ट्रैक पैंट्स पहन लिए थे। Where are you? What was it? That is so pretty. Cute लगी है यार। Brown.
इथे प्रॉब्लेम काय?